Welcome back for the last part of Module 10. We're looking at phase equilibrium, and in particular, we're studying how I can predict the relationship between things such as the temperature and the vapor pressure. And so what we have is we know that Gibbs energy will reach a minimum at equilibrium. And we said that we could take the dg expression, okay, using the fundamental relation, and that's v dp minus s dt. And this will be the same for the alpha phase and the beta phase. If I take this and rearrange, bringing the dp terms together and bringing the dt terms together, and then rewriting this differential as a derivative, then I end up with dp dt is s of the alpha phase minus s of the beta phase over v of the alpha phase minus v of the beta phase. Now, whenever I see S or entropy, I always kind of think, oh, I really don't want to deal with that. So, not a problem. I've got relationships. Our favorite this week is Gibbs energy. So, if I use G equals H minus Ts, the definition of Gibbs energy, then I can solve this for S, okay, and then use the fact that G alpha and G beta are equal to each other. So when I take this and solve for S, I get something that's going to look kind of like H minus G over T. But the G's will be the same for the alpha and the beta phase. So that leads to dp dt equals H alpha minus H beta over V alpha minus V beta, all divided by T. Now this is known as the Clapeyron equation, and it's theoretically true and correct for any two phases in equilibrium. So let's look specifically at liquid and vapor systems. So what are some reasonable assumptions that you could make to simplify this? Well, there are several, but the first one of these is we have the difference between the liquid and the vapor volume. Liquids, the molecules have been pushed together so that they have that close light bonding between molecules that holds them as a liquid phase. For a vapor, the molecules are very far apart, and so the volume of a vapor is much, much larger than the volume of a liquid. Enough so that I could just say the volume of the liquid is essentially zero by comparison. Next thing I can do is I can look at the vapor volume, and I remember that a vapor is a gas, I think ideal gas, so why not try modeling it as an ideal gas? Now this is probably the worst assumption that we make in this derivation. But the volume, the specific volume of my vapor is RT over P. So let's substitute that in. So V liquid minus V vapor is now going to just say RT over P. H liquid minus H vapor is negative enthalpy of vaporization. So delta H vaporization. That negative cancels with my negative from down here. So I get P times heat of vaporization over RT squared is dP dt. We can rearrange this. This is correct. This is a form of the Clausius-Clapeyron equation, but frequently we rearrange it so that it's something with the variables separated. dP over P equals delta H dt over RT squared. I personally prefer this form, but a lot of people will rewrite it then one step further. dP over P equals delta H over R, the derivative of 1 over T, or differential of 1 over T, dt over T squared. This is great, but normally what we do is we go one step further. We're going to take one more assumption. After all, once we made the assumption that the gas phase is an ideal gas, this next one is a no-brainer. Let's assume that the heat of vaporization just doesn't vary with temperature. If I use values of temperature that are nearby, it really won't make any difference. So if I do that and assume this is constant, doesn't vary with temperature, then I can integrate this and end up with this expression here. The natural log of the ratio of vapor pressures is negative delta H over R times the difference between 1 over T2 minus 1 over T1. This is one way to do it if you are dealing with 2 points. Frequently, people prefer to write it as something where they can solve for a formula. And so log of the vapor pressure is minus delta H vape over RT plus a constant of integration. And then we would use that fixed point to solve for the constant. So let's see how we can use the Clausius-Clapeyron equation. We want to estimate the accuracy of this by comparing a predicted value to a measured value. So in this particular case, we are going to use the fixed data point at 0 degrees C. The vapor pressure is 4.743 bars, and the heat of vaporization is 374.5 kilojoules per kilogram. And from that, let's predict the vapor pressure at 4 degrees C and at 60 degrees C. Now we want to be able to compare, so looking up in the data table, we found the values that were measured. So we know these are correct, but let's predict and do a comparison. So at 4 degrees C, plugging the numbers into the formula that we had, we find that the answer is 5.27 bars. The actual answer was 5.35 bars, so we only have a 1.5% error. But notice that the temperatures are very close. 0 degrees versus 4 degrees, very close. If I go to 60 degrees C, a much larger jump in temperature, the prediction isn't as good. The answer comes out to be 17.6 bars compared to 21.2 bars. That's a 17% error. So the assumptions that I've made, the biggest source of error seems to be related to where I use as my fixed starting point, which means that heat of vaporization as constant is the weakest part of our Clausius-Clapeyron equation. Now let's look at one other very commonly used equation. It's the Antoine equation. The Antoine equation starts with the idea of the Clausius-Clapeyron equation. But instead of saying, well, let's rigorously use this fixed constant delta H of vaporization, let's take all of the data that we have available for a material and model it. So this is an empirical equation, but they base it on the form of the Clausius-Clapeyron equation. So the Antoine equation takes the form that the log of P, and sometimes this is log with other bases, particularly log base 10, is a constant minus a number over the temperature. Now they have to usually adjust the temperature, so by adding another constant here, they are able to get this form to work better. And these numbers can be tabulated, the A, B, and C, for many, many substances. So let's look at an example for the Antoine equation. Same example that we did before. This is the formula for the Antoine equation for propane from webbook.nist.gov. NIST is a government agency that is responsible for compiling the best data for substances. So whenever you're looking for an equation or a data source, this website, webbook.nist.gov, is an excellent resource. So this is their recommended equation for the Antoine equation. And again, we're going to just do these predictions at 4 degrees and at 60 degrees. When I do this, the equations I came up with, and this is not written quite right. Log of this is this, but P vape is 5.367 bars. The key thing is it's only a 0.34% error. And at 60 degrees, it's to 4 sig figs identical. So the Antoine equation, because it's fitted to actual data, will actually get you better answers than the Clausius-Clapeyron. The Clapeyron equation was correct theoretically. The Clausius-Clapeyron is weaker because it's made some assumptions, some simplifying assumptions. The Antoine equation is based on the form we get from the Clausius-Clapeyron, but is fitted to data, so really this one typically gets the best results. So at this point, you're prepared to go out and work problems with vapor pressures. You can model all sorts of things using the first and second law, those fundamental relations. We're going to continue our studies of pure substances and how we can solve problems in the next lesson.